Now we move to the second lecture of our morning session, which will be presented by Professor Karstena Meier. Professor Meier is the head of the chair of Inorganic and General Chemistry of Erlangen-Nuremberg University in Germany. He is owner of a large number of different awards, like Alfred Sloan Research Fellowship. He is a lifetime honorary member of Israel Chemical Society. In 2009, he received the Dalton Transaction European Lectureship Award, and at the same year, he was awarded by Japanese Society for the Promotion of Science Award, and he is fellow of the Royal Society of Chemistry. And at the same time, he is a professor of Nagoya University of Technology. Professor Meier, please.
Thank you very much. Is this on? Yes. Okay. Thank you very much for the introduction, Mr. Chairman. And also, I'd like to extend my acknowledgement to the organizers. I feel actually quite honored to be among these esteemed speakers that we have seen here on this conference. In fact, I feel humbled and crumbled. Today's talk is about the electrocatalytic production of hydrogen from water employing F-element-based electrocatalysts. And this talk is dedicated in honor of Mendeleev and the playground that he has produced by developing the periodic table, and everybody else that also contributed to the periodic table, because that was just the start. And so I'm a trained transition metal chemist. I worked with titanium and chromium. Today, it's all about uranium. So I've pretty much made it from here all the way to the bottom of the periodic table. But quite frankly, I embrace all of the elements of the periodic table. I just love this playground, and I hope I can show you some of this chemistry that comes out of that. So a little bit of history. The coordination chemistry, the organometallic chemistry of uranium is a relatively young field of chemistry. The first organometallic compounds of uranium were discovered by Sir Geoffrey Wilkinson when he reported the first cyclopentadienyl compounds of uranium-4 and thorium-4. That was at Harvard University. And on the other side of the United States, at the West Coast, in the laboratories of Streitweiser and Müller-Westerhoff at UC Berkeley, Streitweiser reported this beautiful molecule, so-called uranocene, where two of those cyclooctatetraenide ligands are bound to uranium-4 center. Equally important is a molecule that was thought not to be existent, and this is this tris-CP uranium carbonyl species, also developed and synthesized at UC Berkeley in the laboratories of the late Dick Anderson. Now, both of these molecules have established that uranium centers will engage in covalent bonding, not to the same degree as transition metals do, but to a degree which I believe allows for their fascinating chemistry. Now, a chemistry hero of mine is Jeff Cloak, and Jeff Cloak has employed both of these ligand systems in a trivalent uranium complex. So a COT ligand, the cyclooctatetraenide, and a pentamethyl CP derivative called CP star in uranium-3 is capable of cyclotrimerize carbon monoxide at 1 atmosphere and in a temperature range between low temperature and room temperature. To show you this in a more schematic way, this is now the cyclotrimerized carbon monoxide resulting by reductive activation of carbon monoxide. And so what you do is you form this deltate dianion with this uranium-3 species. Jeff Cloak could also show that if you go away from the pentamethyl CP, but you employ the tetramethyl CP, so you only use one methyl group less, then you don't form the deltate, but the squarate. And furthermore, he could show that when you employ a mixture of carbon monoxide and dihydrogen, you would selectively and quantitatively form methoxide. And the latter reaction is very reminiscent to Fischer-Tropsch catalysis. The problem is, it's all stoichiometric, and that's probably not really desirable. Now, organometallic chemists are pretty fearless when it comes to their starting materials. So they typically start with the yellow cake. It's an ill-defined mixture of uranium oxides. They treat this with hexachloropropene in a fairly devilish reaction with temperatures above 200 degrees Celsius to form this UCl4. That's the starting material. It's an ill-defined starting material that needs to be purified in a transport reaction. And that is a material that never really allowed coordination chemists like me to enter this field. So we were very happy when Dave Clark and Al Zettelberger eventually published a procedure where you start from uranium metal. So up to September 11, 2001, you could actually purchase uranium metal turnings from Alpha Aza chemical suppliers. And when you get them, they are these black oxidized turnings. You would have to wash them with nitric acid. Then you would have to amalgamate them with mercury iodide. Then you get these shiny turnings. These shiny turnings can be immersed in THF and oxidized with iodine to get a very well-defined, nicely soluble solution of uranium trisiodide. That material was only available up to September 11, 2001. Right after the terrorist attack in the US, there is no more source of commercial uranium available. No metal and no oxide. And so being funded by the Los Alamos National Laboratory still provided me with uranium turnings while working at UC San Diego. But when going back to Germany, there was no source of uranium. And so luckily, the city of Erlangen is also the home of a chemical company called Areva. And Areva donated this disc to me. This is 1.4 kilogram of depleted uranium. And then from the Forschungszentrum Jülich, I got this Formstein, 8.5 kilograms of depleted uranium. But when you are a chemist and not an engineer, this is actually quite a challenge because we typically start our materials with like a salt. And how do you transform this into a chemical starting material? Well, we eventually figured out how to drill turnings out of this block. And now, because we drill these turnings in a glove box, now our turnings are beautiful, shiny, and freshly prepared turnings are so reactive that you can immediately take them. You don't have to amalgamate them anymore. You can immediately take them, suspend them in THF, and oxidize them with iodine to get this beautiful material. There's only one slight problem in Europe. We are no longer allowed to use depleted uranium. Instead, we have to use natural uranium, because Germany wants to go green, and hence we use a material that is twice as radioactive as depleted, only because it says natural. So there's a little bit of criticism in this remark, but it makes my life quite difficult because while it is really easy to get depleted uranium in metal form, it is nearly impossible to get natural uranium in metal form. Who in the right mind would actually mine uranium oxide, natural, to actually transform it into a metal?